Well, here we are, differentiating the wave description. How do you feel today, Sam?
I feel all right. Why are you asking?
Well, do you feel wise? Because we need a lot of wisdom when we're
okay.
doing these equations.
I did just got one of my wisdom tooth taken out, so I think 1/4 of my wisdom is gone. But we'll manage.
I think with 3/4 we should be okay.
Okay, yeah.
All right, let's go. So in previous videos, we've established the idea that a forward wave can be represented by a function written like this, f of x minus vt. But let's leave the math aside and get back to physics. So when we have a transmission line, we have voltage with the units of
volts.
So here it is. And let's assume that we have a wave with this function f with an amplitude v plus, and f has an absolute value, maximum value of 1. So this is like the maximum of the wave will have a height of v plus.
So and it's traveling in the forward direction.
And this is a forward wave. So as time increases, x increases. So it's a wave traveling along the x-axis to the right. The other thing we have to consider is current, and the unit of current is?
Amperes.
Now, since the unit of current is amps and the unit of voltage is volts, can we relate somehow I plus to V plus?
Well, yeah, of course. I think from probably high school, we already know V divided by impedance is current. Then you add back your forward traveling wave. Then that's one way to represent the current wave in terms of the voltage wave. Do you agree?
Yeah, absolutely agreed. So now, Sam, I'm going to ask you the question, what equation does the voltage wave have in terms of derivatives as a function of x and t? Well, Sam, before we get the equations, let's write down our expression for the voltage as a function of x and t. So v plus, the amplitude, our function here, f of x minus vt. But I'm going to simplify things a little bit by writing this in a different way. And I got v plus f, this function eta in pink is a function of x and t, and I've just combined this into this function eta. So eta of x and t is a really simple function. It's x minus vt, and v is the velocity of the wave.
So you've just replaced the parameter with one variable.
I've replaced these two variables here by one variable called eta, which depends on x and t.
Great.
So what we have to do now is we have to differentiate v with respect to x and v with respect to t.
What will we get by doing that?
Well, that's what we're going to find out.
Okay.
So the first thing I have to do is ask you some straightforward questions. We're going to need to know what the eta dx is equal to. And let me try to make the tail of the eta longer, like that. The eta dx is equal to?
Well, you get rid of x, and this has no x component, it's 1.
Yeah, the eta dx is equal to 1. And of course, the other thing is
the eta dt.
The eta dt
is just a negative v.
Negative v. Partial derivative. Now, this is going to be your exercise, Sam.
Ooh.
I'm going to ask you, I'll start you off by asking to differentiate dv dx. You'll have to go underneath, and then we'll have dv dt. So take it away.
So, of course, we take the v plus still. I suppose we have a function of eta of x and t. So we need to do some chain rule.
Chain rule, here we go.
Okay, so df, d eta, dx.
Oh, wait a minute. Eta's pink.
Right.
Oh, gotta have pink. Let's get the pink in there so you really see the difference. There's two derivatives.
Thank you.
There you go.
Here, let's hope I don't draw on the shirt. Eta. Good start.
Yeah, great start, except for one thing. Got to go back to this. F is a function of one variable only, eta, and you've got it as a partial.
Oh, so it's actually a big D.
It's a big D,
not big.
not a curly D. So let's fix that up. df d eta. Yeah, that's
now
great.
it's a good start.
Now it's a good start. Okay, so
Okay.
let's finish that off here.
So if we, well, the df d eta, we don't know what it is yet. Whoops.
We got to be the same as last time. This is a really important result here.
Yeah.
We have to be consistent. So df, d, and you got to use pink. Here, have a pink. Oh, you got a pink. Okay, great. Great. So
And we already have a d eta dx. It's just 1.
times 1. Okay, great. Now, I'm going to let you do the next one totally solo.
Wow. I'm ready. I'm
Okay,
Sam
where do you
Solo.
go? Sam Solo, here we go.
dv dt is v plus, again, df d eta, and this time d eta dt, which we already know as well.
Right. Well,
So
we're
we
all
just
in good
substitute
shape.
this with a negative v.
So go ahead, put it all
do it.
together.
Times negative v.
And now here's the creme de la creme, the end of the story. I don't have another color, but I'll use pink. This. Oh, use green. Maybe that's better. V plus df d eta is
V plus-
equal to what?
Actually, this is 1, so it's just equal to dv dx.
That's right. So this thing here, this blob that I've circled in green, actually becomes dv dx. So let's get pink out of here. And this is equal to dv dx times, pink minus v. Minus v, the velocity. So there's our equation. dv dt partial is equal to this. Now, minus v is in pink because it came from eta, but we're going to write the final result in green below, and I'll do that.
And then this is green.
Oh yeah, this is green. See, I got it right. dv dt is equal to minus v dv dx, which we can rearrange. Simple algebraic rearrangement, we get dv dx plus 1 over v dv dt equals to 0.
Wow, this looks like the wave equation to me.
In one dimension, in one direction.
Yes, yes.
So now this is a wave traveling to the right.
Mm.
Can we have a guess of what it would be like if the wave was traveling to the left?
So I guess this is a velocity to one direction. What if we just change the direction of the velocity?
Yeah, so we just make a minus sign here, and that would be waves going to the left.
Beautiful.
And now we can have waves going to the right and waves going to the left. Thanks for your attention.